Now that we've worked with compound interest formulas, we're going to expand and go into exponential growth and decay type problems that use very similar formulas. So we have the growth and decay law is n equals n naught, or n sub 0, times e raised to the kt power. This is equivalent to very similar to a equals p times e raised to the rt power. So if you've gotten enough practice with your compounded continuously formula, PERT, this formula is very much the same. We just use different letters for the parameters. So n is going to stand for the end quantity, So that's going to be the amount we have at the end after a given time, the end quantity after a given time. And again, these letters are not variables. These are called parameters. So we're going to be given some of these values in our problem. They're not going to change for any particular problem. So for instance, your initial amount, so the initial quantity for a given problem will never change. The initial amount is the initial amount. So your initial quantity, which is n sub 0, will be constant in any given problem. However, your end amount usually is the quantity that changes because time changes, and when our time changes, so does our end quantity. So let's talk about time. Time is measured. It's not a number of years like it was with the compound interest with money. Time can be measured, so it's the time that's passed, but time can be measured in whatever you want to measure it in. So seconds, it can be measured in minutes. It's not restricted to just years. It could be days, it could be years, etc. It could be measured in any unit of time. And then K is most like the interest rate. So K is our growth constant. So it's a growth, we call it growth when K is positive. So when it's a positive number, we call it growth. And we call it a decay constant when K is negative. So if K ends up equaling a negative number, it's called a decay constant. Okay, so let's see if we can't use this new formula in a given problem. Here we have the average U.S. per capita income rose from $9,494 in 1980 to $19,696, $19,696 in 1990. So over the course of 10 years, the U.S. per capita income rose $10,000. Now, per capita means per person, so per person working. So that's a big jump. 10,000. That's doubled. That's more than doubled. The income level more than doubled in a 10-year period. It would be nice if that happened in future years, but no, I don't think it's happened in future years. Determine the growth constant. Okay, so let's talk about what they've given us. They gave us an initial value. So this is an initial value right here. So I'm going to call that n naught. And then they gave us an ending value. And I believe I used blue for the ending value. I did. Good. I want to try and be consistent. So our ending value is 19,696. Now by giving us 1980 to 1990, they're telling us that time equals 10 years. So now time is measured in years because it's measured as dictated in the problem. So as dictated in the problem. This is not a compound interest. Even though it's dealing with money, it's not a compound interest problem. So we've got an initial amount, we've got an end amount, we've got a time. What do we not have? Let's write this down. N equals N naught, or N sub 0, times E raised to the KT power. We've got N naught, that value is given to us. We've got time, that value is given to us. And we've got the end quantity, that value is given to us. What do we need to find? We need to find K. Remember that E is a constant. So let's plug it all in. So we've got 19,696 is equal to 9,494 times E raised to the K times 10 power. We're going to divide both sides by 9,494. And we've got this number right here. Don't be nervous about that number. We can put it into our calculator, and we're absolutely going to. We've got E raised to the 10K power equals this fraction. So I'm going to rewrite in log form. So we're going to rewrite in log form. So I've got the natural log, because log base E is natural log. So the natural log of that fraction is equal to 10K, 10 times K. We're going to divide both sides by 10, so K is equal to the natural log of that fraction, whatever that value is, divide it by 10, and that's what K is equal to. So I'm going to put this into my calculator, and I'm going to be able to write the particular equation for this problem. Now let's think about what's changing. Let's think about what's not changing. What is changing? What is not changing? Well, the amount of time. Time is going to continue to go on, right? 1980, 1981, 1990, 1991, 2000. Time continues to pass. So time is going to change. As time changes, so is our end value. The end value is changing. What's not changing is that initial value in 1980. 9,494 is not changing. E is not a variable, so it's staying. Then we have K times T. Well, K, we already know what K is. This K value, that's the value that's going in the exponent. So we're going to put that into our calculator. I'm going to continue to show you this on the calculator just so that you get used to seeing it. The natural log, and then of a fraction, it's 19,696 over 9494. And I'll show you how I do this. I press enter, and then I divide that by 10. So I get 0.072975555493. I'm going to store that value. So I'm going to store it using this arrow key right here. So I hit the arrow, and I'm going to store it as alpha, and then I'm going to look for K. K is right here, it's the comma. So I'm going to store it as alpha K. This way I have the exact value. I'm going to write down 4 decimals though on paper. So 0729. 0729 is going to round up to the next number because 7 tells us that we have to round up. So 0729. 729, the next number is 730. So we're going to write that value down. Notice how I pressed enter. Now, every time I bring up K, it's going to be there. Let's go back to our paper, and on paper we're writing 0.0730. That 0 at the end is very important because 729 rounded up to 730. So 0.0730. And then, what do we have? We have T. Time is going to change. So the particular equation for this problem is given right there. right there. Now we have a model that we can work with. Now we can play with numbers. What if we're only talking about 5 years? What if we talk about 1995? What if we talk about the year 2000? We can put these values in and get values out. According to this model, what will the average income be in the year 2000? Well, $9,494 happened in 1980. We want to know in the year 2000. So that's going to be 20 years later. So time is going to equal 20. So our end value is equal to 9494 times E raised to the 0.0730 times 20 power. However, I'm not going to type in 0.0730 into my calculator. I'm going to use K. So use K in the calculator. So we stored it. It was approximately 0.0730, but we stored it. So we stored the exact value in that calculator. So here we go. Let's try this. We're going to have the initial amount times shift natural log, that's E raised to the, and we want the K20 power. So we're going to have alpha K times 20, all in the exponent. Press enter, and the median or the average income in the year 2000 is $40,860.80 according to this model. So it's approximately $40,860.80 according to this model. If you have the baby Casio, you can still store your value. You're going to hit 9494, then you're going to bring up E, and then it's going to have an upper caret. In parentheses, you have to hit K times 20. Please make sure you put K times 20 in parentheses, and then you will get the same value that I got. Okay, now, according to this model, so now we're going back to that model, when will the average income reach $50,000? So now they're asking us, hey, put a $50,000 in for your end amount and tell us the time. So I'm writing down the 4 decimal place number for K, but when I put that into my calculator, I'm using alpha K, the stored value. I'm going to divide both sides by 9494. You know what's interesting is I remember even taking these classes. When you get the practice, you get so proficient at putting this into your calculator and doing the algebra that it's seamless. The natural log, because log base C is natural log, of 50,000 divided by 9494 is equal to K times T. And remember, your K, this is your K is stored in your calculator. So I'm going to go over to the calculator. And I'm going to say the natural log 50,000 over 9494, enter, divide that by alpha K, and I get 22.766 years. The reason it's years is because years is what was dictated in the problem at the very beginning. So time is approximately 22.766 years. Now, if you got 22.758 years, you used 0.0730. You did not store your value. And that's going to be okay. It's close. 0.758, 0.766. It's very, very close, so I wouldn't get upset or nervous about that. If you had to use 0.0730 because you couldn't figure out how to store the value, definitely ask, how do I store that value? This way you can alleviate that frustration moving forward. We're going to be using lots of exact values on these assignments, so it would be very helpful for you to know how to store values. But if you're struggling with that right now, don't worry about it. If you got the 758 years, you're in very, very good shape. You understand the math. We just need to work on the particulars of how to use that calculator.